All right, we got Unit 3, Lesson 10, Other Conditions for Triangle Similarity. So in Exercise 10.1 Math Talk, Triangle Congruence, they want us to evaluate mentally, is there enough information to determine if the pairs of triangles are congruent? If so, what theorems would you use? If not, what additional piece of information could you use? All right, so if we look at the first example, all right, go ahead and try to figure out why those two uh, triangles are congruent, and if there's a missing piece that would help you prove it. Okay, so hopefully you pause the video and you try to do that one real quick. I notice we have a pair of sides that are marked to be congruent, right? We do have the reflexive property giving us that side to be congruent to itself because both triangles share the same side, right? ln. And what else do they give us? They give us the perpendicular. So okay, that's one. Okay, which means this one is also. So this angle is also congruent. Now, what's interesting is right away, it's like, wait, we've talked about that. That's not a thing, right? So this is two right triangles. So is it HL triangle congruency? Is it? Okay, so we have a hypotenuse to a hypotenuse. We have a leg to a leg, right? So yes, these two triangles are congruent, right? By HL triangle congruence. Now let's take a look at the second one. All right, we have two triangles here, right? We have this one here and this one here. Go ahead and figure out if these two triangles are congruent and by what congruency theorem. And if not, what one piece could you get that would help you in terms of determining whether these two are congruent. Okay, so hopefully you pause the video and you look at this a little bit closer. All right, and let's see, we do have vertical angles here, right? This angle to this angle, right? Angle ACE is congruent, right, to angle BCD, and that's because they're vertical angles. Okay, so that's an angle, pair of angles, right? EC, right? EC is the radius of the circle, and so is DC. So EC is congruent to DC. That's because they're the radius of both of the same circle, right? Now they didn't quite tell us that C is the center of the circle. I'm assuming that. Okay, so that'll give us a pair of sides, and they do tell us that there's a pair of angles. Angle E is congruent to angle D, and that was given. They told us that. So are these two triangles congruent? Yes. Yes. So triangle ACE, and that's based on the assumption that we can use the radius for EC and DC, right? So triangle ACE is going to be congruent to triangle DCB. Okay, and that's angle side angle, triangle congruence. Okay. All right, let's take a look at the next one. All right, got the square there. Okay, with the two triangles. They did give us at least something. All right. And I'm assuming this is a square, but I'm not sure. Could be a diamond. Okay. Go ahead, pause the video, see if you can do it. All right. So hopefully you paused it and you kind of realize that you have a pair of sides that make this kind of help. You have the reflexive property, which definitely helps. They didn't give us any angles though, right? They didn't tell us for a fact that this was a square. Like they didn't tell us IF and HG, right? So we definitely need one more part to be congruent. All right, you can get some angles, but you know, maybe if they gave me IF is congruent to GH, you know, then I would have side side side. So maybe if they gave me that, you know, and like kind of backing up to the last one, maybe if they gave me the radius here, you know, for a fact, then I can definitely know that this is correct or not, right? So it's kind of an assumption at this point. I am assuming that C is the center, right? So notice how it's like, man, I really wish they told me for sure that C was the center of the circle. That would have been very useful. And it would have been very useful if they gave me, you know, that this side here is congruent to this side here, or maybe this angle here is congruent to this angle there. You know, like if they just gave me that one more piece, right, it would have helped. All right, let's take a look at the next one. All right, we got two triangles here. We got this triangle, right, triangle DAC with comparing to triangle BCA. Okay, so we do have two triangles there. All right, go ahead and pause the video and see if you can figure out if these two triangles can be proven to be congruent. Okay, so hopefully pause the video. Let's see, what did they tell us? They told us that AB, all right, is parallel to CD. Means this line here and this line here are parallel. That's good to know. What does that give us? Let's see. They do say, so do you guys see the reflexive property? Right? Both these triangles share AC. So AC is congruent to itself. That's the reflexive property, right? So that's a pair of sides. Nice. Okay, good. They did give us this angle here to that angle there. So we have angle DAC, and they gave that to us, right? So that's the reason why, right? That was given. Now, can we get anything out of the idea that AB is parallel to CD? Can we get alternate interior angles involved? Let's see. Isn't this angle, let me do this in a different color so you can differentiate. Is this angle right here parallel to this angle? I'm sorry, not parallel, congruent to that angle right there, right? And that's alternate interior angles, right? So let's see, alternate interior angles. Let me move some things around so you can see it. So angle BAC is congruent to angle ACD by alternate interior angles, right? And that's really based upon that fact, right? That those two lines are parallel to each other. So are these two triangles congruent? And what theorem? Okay, so hopefully you realize, yes, these two triangles, triangle DAC is definitely congruent. Triangle BCA, and that's by angle, side angle, triangle congruence. Okay, let's move on. That was a good refresher, right? For sure. All right, let's see, 10.2, side angle side. Side angle side, okay. Side angle side, that sounds familiar, right? But instead of congruence, it's similarity. So might be somewhat different. Similar, but a little different, right? All right, so let's see. Andre remembers a lot of ways to prove triangles are congruent, right? We just went through a whole bunch of, triangle congruency examples, right? And then he's asking his study partner, can we use angle side angle to prove triangles are similar? Okay, Claire's like, sure, but we don't need the side part because angle angle is enough to prove triangles are similar. Like my response personally would be like, well, what if they don't give us that other angle? Like what if they only give us one angle? And Andre is basically like, asking the same thing. Like, what if we don't know both the angles? Like, what if we only know like one? And then Claire, she's like, you know what? We're bored. I kind of want to see how that would play out. So she draws a picture so they can start to work on that kind of proof. Okay, because humans do this. They'll get in an argument and they'll literally sit down and do like a proof just to prove uh, who has the better idea, right? Um, that's a normal thing, by the way. So Andre's like, hey, this means corresponding sides at the same length. Then we only get congruent triangles. Wait, if side means corresponding. Okay, so this is the tricky part where they start asking some very specific questions. Like number one, they said, what could side stand for to prove triangles are similar? All right, so notice how in the drawing down below, the sides are not the same length, right? So maybe side means, um, maybe it means like a scaled side. You know, it went through some kind of scale factor, right? It went through a dilation, right? And that's the scale factor, right? So maybe that's what the K means, right? Maybe that's what, like you have Q to K times Q, then you have P, and then that goes to K times P. So maybe that's what it means to be scaled, right? They're both multiplied by the same scale factor, all right? Now let's see, draw a diagram. Looks like we already did that, right? I already, got two triangles down there for you. Let's see. And then now we got to write a proof. So this is going to have to come down to getting A, B, C here to map on to the other triangle, right? So first things first, I'm going to go ahead and I'm going to, let's see, I'm going to go ahead and translate, okay, triangle ABC along the directed line segment of AD. Okay, so what is that going to look like? That'll look like, let me label the sides real quick. This is A, right? And this is B, that's C, wunderbar. So translation would look like this, right? It's going to slide down, right? It's going to translate, shift down along AD, right? So A becomes D. Let me go ahead and do the prime designations, right? That's B prime, C prime now, and A prime. Let me move some things around so you can see it a little bit better. There, very nice. Okay. Now, what do we need to do to get this triangle to undergo the same size? Like, how can we map it on? What's next? Okay, so hopefully you realize dilation, right? So we need to dilate. triangle ABC, or A prime, B prime, C prime, right? The triangle that we just translated, with center A, right? Or A prime, or D if you say like D, right? Because it's like right here that we're trying to project from, right? With scale factor of what, right? So you have AB multiplied by some scale factor to get you DE, right? So let's see here. Would that mean our scale factor is DE over AB, right? And what are we trying to do? We're trying to see if we could do side angle side, but the two sides, notice how the two sides, they're not congruent, right? But what if they go through the same scale factor, right? So that's something to notice right there. So let's see, AC, right, needs to multiply by the scale factor to get us DF. So that means our scale factor would be DF over AC. Okay, so those two have to be the same. Okay, those two, so K is going to have to be the same. So whatever scale factor you get by taking DE divided by AB, it's got to be the same as when you take DF and divide it by AC. Okay, if those two scale factors are the same, then we know for a fact that just maybe this is going to work. Okay, so is there a sequence of rigid motions and dilations that take the triangle ABC to triangle DEF? Yes, right? But the triangles need two pairs of scaled sides and an angle between the between them, right? So like you have angle A for sure, angle D for sure, right? But you have to have the two scaled sides, right? Okay, that's a crazy, crazy, crazy idea, right? You need the same scale factor for sure for both the sides, and you definitely need to know at least one angle. So this would work, right? Because you have a sequence that would get you to get this. Now let me show you the dilation, right? And the dilation will get you right where you need to go. Okay, so that could have worked. All right, prove that these two triangles must be similar. Okay, so let's look. Did they give us any angles? Right? No, but they did give us three scaled sides, which is interesting because now they're giving us side, side, side triangle similarity, unlike side, side, side triangle congruency, right? So scale factors would mean that, let's see, let me trace it. We want ABC, right, to map onto triangle DEF. So let's see. We want triangle ABC to be similar to triangle DEF. Okay, A needs to map onto D. So I'm going to just translate over here. Okay, so that A prime or A maps onto D. B's over here now. C prime is over there. Ooh, notice how it's not really lining up. So I'm going to rotate. Okay, so first things first, translate. Right, we're going to have to translate triangle ABC along A to D, right? Step 2, we're going to have to rotate. Okay, we're going to have to rotate, and then I'm going to have to move this list a little bit over there. out of the way. Okay. We're going to rotate triangle A prime, B prime, C prime. Let's see, we need to get here to here, right? So that's angle C. Okay, so that's this angle. Let's see, so rotate A prime, B prime, C prime with the center of rotation. If I can spell rotation, there we go. At point D. Is that clockwise or counterclockwise? We're going to go counterclockwise, right, against the motion of a clock. So counterclockwise with the angle C prime D F. Okay. What is that going to look like? It's going to look like this. And there we go. Okay. Very nice. All right, let's see. What's next? What do we have to do? So I'm just going to relabel these as double primes, just in case. Okay, and let me redo C here. C's getting a little too unoriented there because of all the rotations, right? Like notice A double prime and B double prime are even, their orientation is sideways now because they just went through the rotation. So let's see. Definitely have to do a dilation, right? Now, do all these sides have to have the same scale factor? Yes, right? So A double prime, B double prime have to be the same as DE for the scaling. Okay, so let me explain. So the scale factor, right? You're going to multiply AB or A double prime, B double prime, right? To get you the length of DE. You're also going to have to do the same thing with the other two sides, right? So the other two sides, right, you want, let's see, B double prime, C double prime to turn into EF, right? And you also want, let's see, A double prime, C double prime to multiply by the same scale factor to get you DF, right? So if you pick a scale factor where they're all going to be the same, that's my alarm. If you're going to have the scale factor to be all the same, then this will work, okay? So let's do the math real quick. Just so you can see what I'm talking about. And this is a proof. Okay, so that's why we're using letters instead of numbers. I know some of you are like, where's the math? This is the proof. Okay, the proof basically acknowledges or verifies that the math all makes sense. Okay, so lastly, we want to dilate triangle A double prime, B double prime, C double prime with center of dilation at point D, all right, or A double prime, right, right here, right, where scale factor is basically going to be the same for all the sides. So that is going to equal that ratio, which is going to equal this ratio. Okay, and that will get you your corresponding proportional sides to all be similar. Okay, so that's the proof right there. Okay. All right, let's move on. In summary, sometimes you don't get, your two angles right away to prove that two triangles are similar. All right, sometimes you'll need to use side angle side similarity theorem, and then again, your two sides here definitely need to be scaled sizes or sides. That means they go through the same scale factor. Okay. If they don't go through the same scale factor for those two sides, can't use side angle side. But if they both go through the same scale factor, they'll work. And then lastly, right, we also went through side triangle similarity. Okay. So if all three pairs of corresponding sides are proportional and use the same scale factor, this is sufficient to prove that these two triangles are similar. Okay, so that's good to know. That's good to know. I know there are some homework questions that are like, here's all the sides, they all go through the same scale factor. Must these be the same? Well, now we can say for sure, yes. Okay, because of side triangle similarity. So that's a nice little update right there to definitely pay attention to. All right, have a beautiful day.